Yes.
You can see it.
Now we can see it.
Okay.
Yeah.
So not all features are equally important. We need to use some techniques. There are lots of techniques which we need to test, and with time you will know how to use. But the most, the simplest one, it's BCA, for example, and the principal component analysis. We can try to find the principal components, the most important features, and it will transform, of course, it from one-dimensional space into another dimensional space with the same dimension, in fact. And we can pick the most important features by sorting the eigenvalues in descending order, right? And we can select the top 5, the top 10, for example. And we can use those top 5 or top 10 for reconstructing the image one more time. And we can see the impact, what kind of information we have. So in this image, not all pixels carry the same amount of information. We can focus on the ones which are in the middle, for example. But in this picture here, for example, images which are close to the edge, maybe it's just white, not images. So it's not very important for us. And then when we use those white pixels into our model, it will make our model more complex. So our model may go for overfitting, and it will require more data, in fact, for training the model. So if we can simplify, if we can reduce the dimension of the features, maybe we can build a model which will perform much better. So we can go to this feature scaling and the normal feature scaling, and we have this data pre-processing, feature engineering, and feature learning. For example, data processing for neural, data processing aims at making the raw data at hand more amenable to neural network. This includes the vectorization, normalization, standardization, handling missing values, and the feature extraction. Handling missing values. Sometimes when you get a data, you have those missing values. So you need to know how to deal with those missing values. Sometimes we can delete a column. For example, imagine that we have a feature and we don't have that much knowledge from this feature. So we have too much missing values in that feature. So we can just delete one feature, or we can delete one example. So for example, you have an example, you have customer data, for example, and for example, in the banking systems, and you have maybe age is missing, gender is missing, income is missing. So you can just decide to delete the whole line, the whole row, for example. Maybe the data, it has an age, and most customers don't prefer to put their age. So we have lots of missing values in this feature. So you can just delete this feature, right? So you can delete a feature, you can delete an example, or you can try to fill in those missing values. So for example, if it is age, you can, and you have, for example, 100 customers, and 10 of them don't provide age. Maybe you can fill those missing values with the average, correct? So there are many ways. You need to read and try to find how can we deal with those missing values. But it's very important to check your data and try to fix those missing values before, because you will get some error. You will get an error if you don't have those missing values not solved. So normalization and standardization, we'll talk about it before. Feature extractions. Feature extraction, we need to extract the most important features. Feature construction, which means we try to create a super feature from the existing features, considering interactions or higher order features and so on. So, it's this feature engineering part, it should be here. We have a model part. This is the model part, and we have our features here. So feature extractions and feature engineering, it should be here, in fact. So we are working with raw data. Maybe from those raw data, we need to use BCA to provide super features. Maybe we need to use feature engineering techniques, feature constructions, and so on. So the feature, engineering part, it should be located here. We are collecting data, raw data. Maybe in those raw data, we have lots of missing values, right? We need to fix it before building or before sending it to our model. So feature engineering should be located in that part. We need to deal with the missing values here. We need to deal with normalization, standardization, and so on before sending those values to the model. Because if you have a missing value, you will get an error in your model, right? So we need to check.
Also removing nodes.
removing
Noise.
noise, of course, yes.
The outliers.
Yes,
Outliers.
yes. But it's also, I mean, when you talk about outliers, it's very critical because maybe it's not outliers, right?
Noise is different from outlier.
It maybe you have a data point, it looks like an outlier, but maybe it's not an outlier. So you need also, because it might be something important. I mean, for example,
Exactly.
yeah, people investing and having startups, maybe they have some range of age. Maybe if someone who's 65 and he decided to have his own startup, maybe it will be considered for the rest of the population as an outlier, but it's not an outlier, right?
Yes, sometimes they cannot build a good model, so they create outliers, and maybe those data are good, but noise basically, fundamentally, is not good for our model.
Yes, but it's for statistical. So there are some statistical tools which are very sensitive to the outliers. And in machine learning also, some models are sensitive and some models are okay with, so we need to decide which model should we use, right? Because I don't know in the future, maybe I will get some outliers in the future to test it and classify it, for example. So you need to decide which model should we use. So
Normally we study the outliers like separately, so that we can be normally we cannot just exclude them as we said, because they can be very important.
yes,
So we have to study them in a separate
yes, correct.
database.
Correct.
Yeah.
So you cannot just remove it because it's statistically it's different from the rest, but you need to check this one. Is it really outlier? Or maybe it's normal data. Yeah.
Since machine learning models don't make any assumption about the distribution of the data, is there still really a need to check for the outliers?
I guess you need to check. I mean, and just to spend some time with your data and check if this one is really outlier or not. And maybe because maybe you have a feature which has a strange range value, for example, so it is considered as an outlier because it will impact if you will use normalization. For example, the maximum value will be different, right? So it will compress the rest of the data in one part. So you need to check it if it is really outlier or not. And bad features may require much more complicated model to achieve the same level. We see it, the same level of performance. Do you see this MNIST? We use that with MNIST today.
Yes.
No. It's for XOR, right? So for XOR, we used feed-forward neural network for solving the same problem, and we can achieve maybe 100% accuracy. And we solved the same problem using feature engineered data, and we can achieve the same results with 3 weights. So the difference was from 81 weights to 3 weights. So you can just compare. I can solve a problem with a model like this huge model, and I can solve the same problem with a small model if I can spend some time with feature engineering. So feature engineering is very, very important. So don't expect, consider this time is wasting time when you are just plotting the data and check the data. Just spend as much time as you want with your data, understand your data, and after that building the model will be just very straightforward. Good feature make the subsequent modeling step easy and resulting in model more capable of completing the desired task. Of course, when we simplify the model, we can build a model which is easy to understand, easy to train. It will be resistant to overfitting and so on. So we need to spend some time with data vectorization. It's important if we have categorical data, for example, right? I have a data feature like this one. I have, for example, orange, apple, banana, for example. My model cannot deal with text data. Even when we are working with text data, we convert text into numbers, right? So we need to convert this one into numbers. So you can just give it some numbers. For example, orange, it will be 1, apple will be 2, banana will be 3, for example. And after that, we can use one-hot encoding. So one-hot encoding is important. So 1, it will be converted into this one. 2, it will be 1 when it's 2. 0 otherwise, and so on. So one-hot encoding is very, very important, right? We have iris dataset. Iris dataset, we have 3 classes. We use the one-hot encoding with it because we have 3 classes. If you will use multi-class using a perceptron or linear regression, for example, no problem. I mean, it's we will use this one versus rest, correct? But if you need to use feed-forward neural network, In this case, we need to use one-hot encoding. So one-hot encoding, very, very important to convert the categorical values into numerical values, right? So this is very, very important. So scaling and normalization, it's very, very important. You talk about distribution of data. Is it normal distribution or? So I mean, it's just recommended to standardize your data set. So all vectors are standardized, have the same Gaussian distribution with the same mean, with the same variance, right? So standardization, it's we can use for scaling, for example, we can use min-max scaling. So we need to put all features between 0 and 1. It's very, very important. Very important. Why? It's because of the activation function, nothing more. So I just mentioned it here. If you have the activation function like this one, we have an activation function, for example, Gaussian. So it will be like this one. So what is the input to this one, in fact? It's net, it's omega x plus b, right? So you have the features, multiplying those features by some omega values, plus bias, it will be very large, it will be different. In fact, it will be a vector. So I have x vector. When we do this one, it will be another vector. But those numbers will be very huge numbers. So imagine we are talking about income and age. So the age here, or gender, for example, gender it's 1 and 0, for example. So maybe male is 1 and the female is 0, for example, correct? And the income, it's in 10 million of krona. Age, maybe it's number between 10 and 50 or 10 and 60, for example. So those numbers will be multiplied by weird values. So those numbers will still the same. Some numbers are very high, some numbers are very small. So when we feed those numbers to the activation function, some numbers will be close to here, some other numbers will be here, right? So imagine it's income. So someone, his income is 10 million, so he will be located here. So someone, his income is 500,000, he will be here. But both of them will be converted into one, right? Because in this case, we lose information. We lose the variation in my data set, right? But if we will normalize it, for example, all those numbers will be between 0 and 1. So the one who is earning 10 million, he will be here. The one who is earning 4.5 million, he will be here. And the rest of the people will be in between. So in this case, we keep all variations in my data set. But if you didn't normalize, you will lose lots of information. Your model will not see the changes in the and it's the same for age, it's the same for gender, for example, and so on. So it's important to have all features in the same range, so the model can feel the variations in my features. Because when we use BCA, for example, we try to select the feature which carry lots of variations. Now, without normalization, we chop this one out, right? Because this activation function has this squashing impact. But remember, this is the activation function which does this. If you will use ReLU, for example, what will happen? So ReLU, it's like this one. So all X values will be converted to the same values, correct? So we don't have this problem here. So if you will use ReLU, don't normalize. We don't need to normalize, correct? So just use it as it is. All positive values will be converted into the same values, but all negative values will be converted to 0. But we use this one usually with images, and the pixel value, we don't have any negative pixel values. So it will not be. So in deep learning, we don't normalize, we don't standardize, we just work with the raw data. Because we have activation function which will deal with this situation. But if you are using a Gaussian, for example, right? So in this case, no, we need to normalize, we need to standardize. But in deep learning, we don't need to do this.
For example, in case the negative number matters, for example, we are predicting credit scoring, and the guy, he has debt.
Yes, so we have another version of ReLU. What is the name of it? Can you check? Which has part here, negative, consider negative values. Can you check its name?
I don't know, but
so you cannot use ReLU, you need to use the other one, in fact, right? Or
There is a parametric.
Parametric ReLU?
Yeah.
Yes, maybe this is the one. So you can just use another activation function.
PRELU.
Hmm?
PRELU. PRELU.
Parametric RELU. Okay, so parametric
Parametric, yeah.
Parametric RELU. So you can use this one, for example, but also because we can handle the data. So you can decide what will be the negative value. But I can normalize my data set. So now when we normalize it between 0 and 1, we assume that the small value will be 0. But you can shift, correct? You can shift my data points. So all negative values, it can move to positive by, correct?
Do you think, yeah, in practicality, do you think it's better to avoid this sigmoid that squashes the number? It's better to use this advanced one RELU?
Yes. You need
to keep the knowledge,
I guess you need to stick to, the first hidden layer, you need to use RELU. Because the first one, this is the one which will deal with the raw data. But also if you will use it, the second one also, it will be a problem also. So maybe if you will use RELU, you can use RELU on your hidden layers, all hidden layers. It will be much better than sigmoid. It's also because of the vanishing gradient, right? Vanishing gradient, it's a problem. When you go more deep, when you increase the number of hidden layers, the gradient which we use for updating, maybe next week we will discuss about backpropagation, but the gradient each time it's multiplications. When we go backward and multiply all times, when we have this one, the first derivative of this one will be something like this one. Because we use the first derivative. Do you know? Delta omega equal minus eta multiplied by partial E by partial omega. So this one, in fact, this one will be function of the activation function. So we need to get the first derivative of the activation function. When it's a sigmoid, the first derivative will be something like this one. And this number, in fact, it's maybe 0.1 or 0.2. So it's much smaller, in fact. And when you have multiple hidden layers, you multiply this one several times, so it will be really very, very, very small. So the gradient, when we try to update the weights of maybe the input layer, for example, the gradient will be very, very small, close to 0. So when this one close to 0, delta omega will be 0. So we will not update the weights. So you will update maybe the, we go backward and adjust maybe the second hidden layer. When you go to the first hidden layer, for example, maybe those values will be very, very small, and we will not update the weights. We will keep the random values, which we started with. And imagine you have some features, and you just multiply those features by random values, so it will be random values. So imagine you are working with images and multiply those images with random numbers. It will be random numbers. It will not image anymore. So it will be something which is not related to the problem, in fact. So vanishing gradient is a problem. How can we deal with it? Using maybe RELU, parametric RELU, because the first derivative of the RELU, it's Gaussian, right? So it's number between 0 and 1. So the performance of RELU will be much better, in fact, than Gaussian with a vanishing gradient problem. So it's a problem. But anyway, if you are working with if you are working with shallow learning or deep learning, just try to avoid Gaussian, for example. If you cannot avoid Gaussian, you need to standardize and normalize your data, and you can just compare it. For example, train your model with iris dataset with normalized and compare the difference in the accuracy. You will see big difference, in fact, in the accuracy, just normalizing this simple problem. And imagine, especially for you have data sets from banking systems and the income and lots of numbers. It will have lots of impact in your trading.
Still, if we are using the parametric RELU, do we still have to normalize and standardize to a
No,
certain extent?
no, you don't need.
No.
If you want to do it, just do it.
Okay.
But deep learning, they do deep learning, in fact, for dealing with those. But in fact, deep learning, it meant for working with images. Because you can work with any numbers, but the plan was, the idea was to work with images, because we have lots of images, lots of data around us, and it's impossible for us to go to those data and try to fix it. So the idea was to work with raw data instead of pre-processed data, in fact. But if you need to spend some time with the data, it's fine, you are welcome, right? Your model will be much happy, in fact, if you can spend little time with the data and try to fix your data for your model. It will be, the performance will be much better. So instead of training your model in 10 hours, it will take 2 hours, for example. Instead of getting a performance of 70%, it will be 80%, 85%. So, but if you will work with images, for example, And if you will use ReLU, there is no need, in fact, to do anything. Even here in MNIST data set, we normalize it, we divide it by 255. We divide each pixel value by the range. If you will work with ReLU, there is no need, in fact. Don't do it. Don't waste your time, right? But it's not wasting of time at the end also, I mean. So standardizing, we need we assume, by the way, we assume that all data are coming from normal distribution. We will try to push all features to have a mean value of 0 and the standard deviation of sigma. So normalizing each feature independently to have a mean of 0, and normalize each feature independently to have standard deviation of 1. We need to get sigma of 1, standard deviation of 1, and the mean value of 0. So this one will be very good. And if in case of standardization, you will keep negative values, I mean. So all positive values will be positive, negative values will be negative. But it will have a mean value of 0 and a standard deviation of 1. It's different from normalization. Normalization, we use min-max scaling, so we need to make it between 0 and 1. If you want to make it between -1 and 1, you can do it, right? Because we assume that we define minimum value equal 0. You can select minimum value equal -1, right? So because we divide here by the range, it's x minus minimum divided by the range. So we will put it between 0 and 1. So you can put it between -1 and 1, right? So we can put it between -1 and 1, and even also when in initializing the weights, we usually select numbers between 0 and 1. You can select between -1 and 1, right? So it could be. Standardization, it's a variance scaling. It's x minus mean divided by standard deviation, right? So it will be like this one. There are many ways also for L square normalization, for example. It's dividing the original feature by its Euclidean norm, right? So if you have a data like this one, when you use L2 normalization, it will be a circle, right? Because you're dividing it by the norm of each feature, by the whole feature, right? So it's x divided by the summation of x1 squared plus x2 squared plus xn squared. So interaction, I have been talking about those feature construction. Feature construction, we can use higher order features, and also we can try to get those interactions between features. So for example, I can have this decision line, for example, if I'm working with x1, x2, and xn, for example, and if you want to consider interaction. So you need to find all possible combinations of interactions and test it. So it's time consuming, in fact. And there are lots of optimization algorithms which do it for us. So for example, I will use this is the same part, but I will use x1 times x2, x1 times x2, right? x1 times x3, x1 times x2 squared, x1 times x3 squared. You can try all possible combinations. It's time consuming process to find those interactions, which one is important, which one is not important. And you will find maybe correlation coefficient, and you will select the one which really carries some information, some knowledge. Maybe x1 times x2, it has a meaning compared to x1 alone and x2 alone. So in this case, I will just use x1 and x2. So you can do it like this one, and there are some techniques to find which one is superior, right? So there are some optimization algorithms. I mean, feature engineering, it's a branch by itself. To work with those feature engineering and try to, but there are lots of tools, in fact, which we can use for finding the best interactions and the most powerful interaction. The most important for us is to get a superior feature which can help us to solve the system, the data, using a simple model, as we did before with those make circle, right? So when we used the x1 squared and the x2 squared, it helped us to simplify the model and solve it using a perceptron. For the x-or problem, instead of working with x1 and x2, we used x1 and x1 times x2, and it helped us to simplify the data set a lot. So feature interaction, it's combinations of pairs of input features. Interaction features provide more accuracy above single tone features. So maybe this one, will perform much better than each single tune feature, right? So, but maybe it requires some domain knowledge to propose what kind of interactions should we use. You can just use it in a blind way. For example, you can just make an algorithm, and the algorithm will try all different combinations. Maybe you can use genetic programming, right? Because genetic programming, the input will be x1 and x2 and xn, for example, and it will try all different multiplications and the power and so on. Do you know how genetic programming works? So in genetic programming, you need to define, it generate an equation, correct?
Yeah.
So you have some features, x1, x2, x3, for example, and I will define the operator, which we need to use, maybe multiplications and the square root and the power, and it will use those operations, and it will try all different possible combinations to generate a new equation, which will represent, my data, for example, or, so it will try all different possible combinations, and you will test it, and you will select the most powerful ones for representing your data and solving your data.
And for sorry for using a technique for a negative value, there is a technique flexible ReLU.
ReLU.
Yes.
Yes.
Flexible. Yes.
Which is like
Yes, for negative.
yes.
Flexible
Yeah.
ReLU.
Yeah. So
Parametric is not good as this one.
because parametric, it has non-linearity.
Yeah.
So this it's like
Flexible.
it's like this.
Defined linear.
Yes,
Yeah.
linear. Yeah, it's linear, but parametric, it's not linear.
Yeah.
In the negative part. Yes, correct. So it's hyperparameter, in fact, hyperparameter. So we just need to test which one will work better for you, which one will give you better results, and so on.
Well, in my opinion, when we are using a machine learning techniques, it is better to create a loop and use a lot of.
So the grid search, for example, I can define number of activation functions. For the learning grid, for example, I can define numbers, a set of numbers which I need to test. Number of hidden layers, the number of units in each hidden layer, and you can just let it work and test all possible combinations.
Just takes time.
It takes time. So you need to have a powerful computer, in fact, or a work machine with a good GPU, for example, to test all those combinations. And it will be nice. We try to get a server for our simulation and visualization so people can test those time-consuming stuff. Yes, so missing values. We have been talking about those missing values. And as I told you, the first step, if you have a feature and you have lots of missing values in this feature, so just remove it, right? Not waste of time, because if you have a feature and if you have 100 points and you have only 10 people answered this one, so just ignore it. Maybe it's not important. If you have 100 customers, because each row is a customer, right? And you have one customer who didn't provide too much information. So we have many missing values in this line. So just delete this line. If it is expensive to delete, for example, if it is important, if you have only few people who has been answering, so in this case, I need to keep him. So you can fill missing values. And there are lots of techniques if you should fill it with average value or mean value, or mean and average, it's the same. We have average, we have mode, for example, so you can median, for example. Yeah. So you need to know how can we fill in those missing values. But it's very important to, when you feed those points to the model, you should not have any missing values. But we are happy also because in Python, there are lots of techniques which can deal with those missing values and fix it for you. Feature engineering, we'll talk about feature engineering. Feature engineering used to be critical because classical shallow algorithms do not have the ability to learn useful features by themselves. Yes, in shallow learning, we need to provide those features. But in deep learning, in fact, the first few layers, in deep learning, in convolutional neural network, for example, so the first part, it's for feature extraction. And the second part, it's for, we call it dense layers. So we have convolutional layers and we have dense layers. Those convolutional layers, it's for feature extraction, correct? So it will by itself try to extract feature by itself. It will try to find useful information from the raw data and send it to the dense layers for decision making. So the first part, it will be in charge of feature extraction. But in shallow learning here, we don't have that part. we need to provide good features for our model. So we need to pay attention to which features, which values we need to provide. So we need to do it manually, in fact. But in deep learning, we don't need to do anything because we have a part. I mean, the first part, first few layers, for example, it will be working for feature extraction. But in shallow learning, we need to try to identify the most important features. And also we need to use feature engineering to try to extract or create new features, superior features, use BCE to use principal components, right? So we need to work a little bit with features. But in deep learning, we don't need to do this. So feature engineering, for example, it's an example, I found it in a book, and it's a very good example, for example. So this one, we have those raw data. We need to build a machine learning to read time, for example, from an image, right? So if you are working with deep learning, I can just send this image because this one has fixed pixel values. It's a black and white. So I can just send this one to the convolutional neural network as it is. So convolutional neural network, you can work with raw data, right? Because it will be able to extract features by itself. Maybe it will be more clever than us, in fact, because it will be more capable for creating those filters and scans the image and try to extract features layer by layer. It will try to find the high-level features from this one, and it will use this one for decision making, for reading the time, right? So I will just feed it with those raw data, pixel grid, for example, and the output will be the time. I will read the time. So I will train it to read the time from the image, right? So in CNN, we don't have a problem. It will work with raw data. For MLB, for example, if we need to use feed forward, it's a shallow learning, feed forward. So we cannot work with this one. Maybe this one will be too complex. It will be very, I can use this one, but maybe I need a huge data set to train my model. It's like an MNIST data set. In MNIST data set, we have been working with pixel by pixel. But do you see here, we will have lots of pixels which will not have any information. All those pixel values will not have any information. So my model will be very complex. And we need huge data for training it, which might be impossible. Because I need to collect images and to just write what is the target time, what is the time now in each image. So I need to do it maybe for each second, and it will be a very huge data set. So it will be impractical for multi-layer perceptron. But for multi-layer perceptron, if we can just get, for example, XY coordinates for each clock hand. So I just need to get this coordinate. From this coordinate, I can just, so in this case, in fact, if I will use coordinates of the clock hands, I have x1, x2, y1, and y2. So in this case, I can build MLB using 4 inputs, right? And it will do the same process. So I just need the XY coordinates for the clock hands. So in this case, in case of MLB, the MLB will has 4 inputs, right? And it will solve the same problem, like CNN. So in case of CNN, we don't care. I can just send the whole image to CNN and it will take care of it. But in MLB, I need to find an algorithm, and this algorithm will try to find the XY coordinates of X handle. And my MLB, it will be more simple now because I will send, it will has 4 inputs, X1, X2, Y1, and Y2, right? So it will be much easy. But if you want to solve the same problem using a perceptron, so the perceptron is much simple. So what kind of knowledge we need? I can just get this angle, θ1 and θ2. So now it will be the perceptron with 2 inputs, right? So if it is MLB, I need to get maybe the coordinates of each clock handle. So I will have 4 features. If you will solve the same problem using a perceptron, good features will be θ1 and θ2, this angle, right? It's the angle between the x-axis and the handle, right? So in this case, I can solve the same problem. So this is how can we deal with features. If you will develop a CNN model, for example, don't worry, just feed it with all raw data and it will take care of it. If you will build MLB, now we need to work a little bit with the features and we try to get some useful features from the image. For example, I can get the coordinates of each XY coordinates of each handle, right? If you will develop a perceptron, it will be more tough, in fact. Now I need to get something more simple for my perceptron, maybe just θ1 and θ2. So it will map theta1 and theta2 into time. This one, it will map x1 and x2 the xy coordinates into time. This one, it will use the raw image for identifying the time. This one, we need large data set for it to train, right? Because this one will be more complex. We will have many parameters here, so we need larger data set, in fact, to train this model. This one, it will be much less. This one, it will be much, much less. So feature engineering and feature selection is very, very important. Yes. Any questions?
Just one question. Ravi here. So from what I understand is CNN needs no input features because it comes up with its own features in the hidden layers. MLP, we need to give some generic features, and perceptron, we need to give very precise features for it to work, because perceptron is a very simple model. So is that right? That's correct?
Yes, correct. Yeah, it's correct.
Okay, so so CNN is working out its own features, like because of its dense network, it's figuring out its own features. It's somewhere in the hidden layers, right?
Yeah, we feed it with the raw data, and it will try to extract some feature from those raw data, right?
Okay.
Yeah,
so
yes.
Is it possible for us to see those features? Like, what is it figuring out? Like, is there any library method which tells us, okay, this is these are the features that the CNN has come up with, or it's just like we have to just depend on its output only to evaluate it?
I mean, if you will be working with deep learning, you don't need to worry about it. Just feed it with raw data, right? Just feed it with your raw data, no problem. Don't care about it. It will try to extract high-level features from those images by itself.
Okay.
But in case of shallow learning, you need to work with the features, because I can feed the same image. This image I can feed it to MLB, but MLB will be made more complex. Imagine MNIST dataset, it has 784 pixel values. So this one also maybe will be the same. But imagine if this one, it's something more complex. If it is a scene from a movie, for example, it will be really more complex. It will be impossible to train MLB using this one, because what kind of features from our mind? Because the idea of features, we can use extract some features manually, and using those features for training my model. But the set of features which you are imagine, maybe it's not useful for the problem. But in case of deep learning, we will let it try to figure out those features by itself. And it will be a huge set. It will be huge, really. So we will use this one, and we will get a feature map. We will try to get high-level features from the low-level feature maps until we reach. We need more data. We need more time for training. We need a powerful computer, for example. I can train shallow learning in my CPU, but if you will train a deep learning model, maybe it will take too much time in your CPU, and you need maybe a powerful GPU, for example. So it's data. I mean, in deep learning, we need data. We need more data, more time, more powerful computer, computational resources. But in case of shallow learning, it's just simple. I mean, but we need to spend some time with features and try to get the most important features for us. Yes, in deep learning, do we need to still work with features in deep learning? I mean, people say yes, we need to do it. I mean, if it is useful for shallow learning, it should be useful also for deep learning. So if you can do some feature engineering also a little bit for deep learning, it will be nice. It's not bad. So good features still allow you to solve the problems more efficiently while using fewer resources. So it would be, so I mean, if you can spend some time with feature engineering also with deep learning, it's fine, but it's not very necessarily. Overfitting and underfitting, we'll talk about it several times before. What is the difference between overfitting and underfitting?
When the prediction is high on training and low in testing, it's overfitting.
Overfitting. So the data will overfit your data if the model is really very complex and the data is simple. So it will just memorize the data points, and it will not be able to generalize. How can we discover it? Maybe from the accuracy prediction error, for example, from the testing and the training, right? So we can discover if we have overfitting or not. Underfitting, it's not a problem. It's something very healthy, in fact. We build a model, and if we feel that it's underfitting my data, I just make it more complex, right? We just increase number of hidden layers. It means we need to increase the model complexity, the model capacity, in fact. How can we increase the model capacity? By increasing number of hidden layers, number of units in each hidden layer to make it more complex. So it should be more capable of mapping inputs into outputs. So underfitting, it's something very good. Usually, in fact, in machine learning, you start with a basic model, with a simple one. And after that, you will increase complexity step by step until you have good performance.
In underfitting, normally the accuracy of the training is very bad from the beginning.
Both are bad in training and testing.
Okay.
Both are bad, which means it's indications that I need to make it more complex. It cannot understand it cannot map inputs into outputs. So I need to make it really more complex.
I think in this case, maybe it can never happen, but can you imagine like you have bad accuracy or average accuracy in training, but very good in testing?
No, it's impossible.
It's impossible.
It's impossible, yes. Yeah. For example, for MNIST data set, for example, we can start with a model with one hidden layer and 5 units in the hidden layer. So I should expect that it will not work well in both training and testing. So I can increase the number of units in hidden layer into 20, for example. So increase it a little bit step by step until you have good accuracy. You will see the performance, in fact. So underfitting, it's not a problem, but overfitting, it's very dangerous. Because I remember, in fact, long time ago, some master students they started working with machine learning and building those feed-forward neural network, and they just are very happy with 99% accuracy. But it's overfitting. It memorizes the data, but it will not generalize. So the performance will be really very bad when you deploy it in real life. So overfitting, it's a very dangerous problem. How can we fight? How can we solve this overfitting problem? We just agree that overfitting means the model has higher capacity, right? Or the data set is not good enough, big enough. So one way is to extend the data set, right? We need to enlarge the data set. There are some techniques for doing this, especially if you are working with images, right? If you are working with images, we can use some image processing techniques to extend the size of my data set, duplicate it, for example. One other way, for example, is to put some restrictions on the model itself. I need to stop the model before overfitting. So we have a technique called early stopping. So we will be watching the accuracy of in the training and the validation, and from this one we have an early stopping technique to stop the model before, because overfitting means the model is we keep training the model until it's overfit. If we can stop it early before overfitting, some few epochs before overfitting, so it will be okay, right? Because the model capacity is very high, and we keep training the model. If you keep training the model, it will memorize the data. We need to stop it before this stage. So there are some technical programming approaches. So you can just watch. The validation accuracy and the training accuracy. And then when you feel that it goes to overfitting, you can go backward, maybe 2 epochs earlier. In this case, we need to store the weights, right? Because I need to go back maybe 2 epochs or 5 epochs backwards. Because now I'm overfitting, so I need to go back. How can we go back? So we will keep training the model, and we need to store maybe the weights in the previous maybe 2 epochs or something. And then when we feel that now we are going into overfit, we will just stop training, right? It's like, in testing, for example, I give you very small 2 pages, for example, and I told you, okay, you will take an exam next week. It's too much time, so you will just memorize it very quickly. So if I really want to test you, I can just say, okay, you have those 2 pages for 2 hours, and you will take an exam after 2 hours. In this case, maybe you will get B, right? Maybe C, B. But if I give you the 2 pages and I told you after 10 days you will take the exam, you will just get A, right? Because like doing a quiz in the classroom, for example. So it's like a quiz. You will do a quiz here, or the same quiz, you will do it after 10 days, for example. You will get just A. Because it's simple, and you are more capable. You have enough time for training. So we'll just memorize this, for example. So we have early stopping. For example, early stopping, it's a very important technique. right? And we have also L1 and L2 regularization techniques. We try to put some restrictions on the weights. What values should we will update the weights, but until what? We will change the objective function, the cost function. We will add maybe in L1 and L2, we have the absolute value, summation of absolute value of weights or summation of square values of weights. So we put some restrictions. We try to minimize the summation of weights. We don't want those weights to take any values, because if you are training your model, by the way, those weights, and if you keep training your model, maybe some of those weight values will keep increasing until at some point it will do some feature selection by itself, right? So if I have some inputs to my feed-forward neural network and one weight increased a lot, so the feature which is connected to this weight, it will take more importance, in fact, compared to the rest. So the neural network now, it will select features, it will do some feature selection, and it will use some features, and it will focus on some specific features for making a classification, for example, and it will ignore the rest, right? So it will do some feature selection by itself, and it will overfit those features, for example. How can we stop it from doing this? By putting some restrictions on the value of the weights. We cannot allow the weights to just increase to infinity. We can put some restriction on the weight values. So in this case, we will stop it from doing those feature selection.
But doesn't this increase the chance of fading weights?
Of,
Fading weights in the layers. The weights are fading. Doesn't this increase the chance?
What do you mean by fading weights?
That if you have a lot of layers and the weights are low, in each epoch the weights become lower and lower, and it fades almost.
Vanishing.
Vanishing, you
Vanishing.
No, because vanishing, it's connected with the first derivative of the error, with the cost function. So the cost function here, it will be mean square error, for example, right? So it's connected with the cost function.
Yeah.
The last technique that you were speaking about, it's called L1, L2 regularization for the weights.
Yes, because we have L1 and L2, but we need to test it. So for example, most common regularization techniques for overfitting problems is reducing the network size and the size reduction, for example, adding a weight regularization and adding dropout, for example, and early stopping. Number 4, it's maybe early stopping, for example. So, for example, how can we reduce the network size? I have my network, right? So, and I have all those weights. Imagine that it's a full neural network like this one. So one way for reducing the model capacity is to use this dropout, correct? When we use dropout, for example, we will drop out some nodes with the connections, with the weights which are connected to it, correct? So we use it in the training. So you have the neural network, right? And I need to reduce the capacity of the model. So in the training process, we drop out some nodes, and when we drop out some nodes, we stop the weights which are connected to those nodes from adjusting from training. We stop training part of it. So imagine that this dropout, it's 0.5, which is 50%. So in the training process, each time in each epoch, for example, we will drop out 50% of the nodes and the weights which are connected to it. So we will not train it in each phase, for example. We will train only 50% of the model weights, and the rest will just stay as it is. So it's a kind of try to reduce the model capacity to make it just not very powerful and progressive. Because sometimes when it's very progressive and it will just memorize the data very quickly. So we try to use dropout, for example, use L1 and L2. So for example, if we're adding the part here, so this is the cost function, which we try to minimize. We try to minimize the error between the target and the predicted, correct? We try to minimize this one. If we add this lambda multiplied by the summation of omega squared, for example.
So this is analogous to lasso?
Yes.
Okay.
Yeah. So we will try to minimize the summation of weights. So we will try to stop it from, getting higher values. We'll try to stop it or hinder it from getting higher values. So in this case, delta omega will be this one. And this is the original part, which we used in error backpropagation. We will use it next week, right? But we will add the part to it. Lambda, it's a regularization coefficient multiplied by this omega value. So we try to minimize those weights or don't allow it to increase to infinity from lambda by adding the part to the cost function. So because we will minimize this part. So we are minimizing the error and at the same time minimize the weights. We don't allow it to expand to any values. So sometimes it's a summation of omega square or summation of absolute value of omega. So it's L1 and L2. You just need to find what is the difference between L1 and L2.
Yeah, that's what I was going to ask. What's the main difference between L1 and L2?
In fact, it's when it's I guess when it's absolute value, we will get something called the sparsity network. So some of those weights will be zeros, right? So I mean when you use omega square, you will try to minimize its because when it's omega squared, when you have small values, it will be more sensitive for small values, correct?
Yeah. Because when you square the small values become even smaller.
It will be more smaller. So it will try anyway. You will get a neural network with lots of small values. When you use absolute, many values will become zero.
When we use the square, the many values become zero. If you use the absolute, then we have small, like ridge regression.
Yes, so this is the difference. So when many weight values will go to zero, it will be sparsity. I guess they call it sparsity neural network or something. So many weights will be zeros. You will lose many connection here. You will simplify it a lot. Because when a weight value is zero, it means we lose some connection. So you will simplify the model, right? So just use the most important features. So for example, so when imagine this weight value becomes a zero, for example. So don't have this connection. We will lose many connections. In fact, so the weight matrix, if it's omega, for example, equal if we have a matrix of weights, lots of values will be zeros. So anyway, at the end, we will reduce the model capacity for overfitting my data set. And in this case, we can build a model which can generalize, not memorizing my data points. So size reduction, it's a simple way to prevent overfitting. And it's to reduce the size of the model, the number of learnable parameters in the model, which is determined by number of layers. The number of learnable parameters is often referred to as model capacity. A model with more parameters has more capacity, in fact, and more chance for overfit. So this is the curve which we need to see, in fact. So we have this. So the smaller network, we have a neural network here. So this is the original model, in fact, this one. So this one, it's the original model. And when we use, okay, we have a model and we have a smaller model, right? So this is the original model, correct? And you have a smaller model. And this is the validation loss. When you have a smaller model, less capacity, right? So it will not. I mean, the validation loss. In fact, it's much less for the smaller model. So it's. I mean, the chances to overfit when the model is smaller or reduced will be much better. So. If you want to try a bigger model, for example, so you have this one, the original model, and you have a bigger model. So when it's a bigger model, it does not mean that the performance will be much better. So in fact, the performance will be much worse, correct? So we need to select the optimum model. So this is a comparison between a smaller model and a larger model. We add this L1 and the L2. So L1 norm. Loss function is known as least absolute error. This is the, I mean, it's just a comparison between L1 and L2. So you need to what is the difference if we will use absolute or if we will use a square difference or square value. So this is L1 and L2. We need to implement it. I mean, in fact, next week I implemented error backpropagation, but I didn't add L1 and L2. So we can add L1 and L2, and we can test drop out also. So drop out, it's funny stuff, and it's very nice, especially in convolutional neural network. So in fact, in drop out, we generate a probability value for each node. In fact, we generate a random value or probability value. And then when this probability value is greater than or equal to some threshold value, we can drop out this one, right? We can drop out this node. And when we drop it out, in fact, we go forward for calculating the input, the output. So we consider it when we go forward, we have the full neural network. But when we go backward for adjusting the weights, we will not adjust the weights which are connected to the dropped out nodes. So this is the idea here. It's a technically just some, I mean, implementing it, it's a technique. You need to do it in your implementation, in fact. But in MATLAB, in Python, in fact, we just have dropout. You just select a dropout coefficient, and you can just do it. But in dropout, when we go forward, we use the whole neural network for calculating the output. And when we go backward for adjusting the weights, we ignore the weights which are connected to the dropped out nodes. We don't adjust it. So in this case, we train maybe 50% of the model, or maybe 40% or 60% of the model. Feature selection. Feature selection is it enables the machine learning algorithm to train faster. It reduces the complexity of the model and makes it easier to interpret. It improves the accuracy of the model, and it reduces overfitting, right? So I want to go to this code, but also you can go to this GitHub, please. Try to open this one and try to, it's an example for feature selection. It's a tool, in fact, it's called select k-best. K is a number, in fact, it's integer number. So for example, if you have 10 features, you need to select the best 2 or the best 3. So K, you need to specify K. So it's a tool for feature selection, and it's a statistical tool. And it's from sklearn. We can just import sklearn from feature selection. It's called the select k-best. There are many, in fact. There are many approaches, but this is one example. So for example, in Iris dataset, you can apply this one to Iris dataset. In Iris dataset, we have 4 features, but we don't know. Maybe someone mentioned today or online, he said, we just used, I mean, we just select last time beta length and width, and one time sepal length and width. I did it, in fact, just by random, because I don't know which one is important, right? But how can we know which one is important? We can use this select k-best. So select k-best, it's a tool, statistical tool, which help us to select the most important features from a set of features. You can just Google select k-best, and you can know, I mean, you can just Google it and try to find what are the inputs, what are the arguments, how the algorithm works. In fact, it's based on maybe Fisher scores or chi-square. It's a statistical tool, in fact, based on chi-square. It could be chi-square or it could be Fisher scores. It's a statistical tool for calculating correlations and variation and stuff like this. So, and I used it with Iris dataset because when we started working with Iris, I just picked 2 features. I selected 2, in fact, because I want to visualize it in 2-dimensional space. But which 2 is best? Which 2 is better? I don't know. I just picked 2 by random, in fact. So one time I used the beta length and beta width, I guess. One time I used the beta length and the sepal width. So just by random. So if you have 4 features in this dataset, which 2 should we select, or which 3 should we select? If you have MNIST dataset and we have 784 pixel values, which if you want to work with 50, which 50 should we select? So this tool, in fact, it will calculate it will return to us the key top features with the highest score, So in fact, so I loaded here the iris data set. I need to select two features with top two chi-square scores. So I just, it's for example, it's for the feature, of course. So we just we define a selector, and we select X new. X new, it will be the new features, the new set of features which we will get from this one. And we can also display the scores. So all scores, I have 4 features. So each one has a score. In fact, this chi-square, I selected chi-square. So it will be 10.8 for the first, 3.7 for the second, 116.3 for the third, 67.04 for the fourth. And I need to select the 2 top features, right? So in this case, I will select this one and this one. This one, it's better length, better width, Symbol length and symbol width. So it's smart to work with symbol length and symbol width, right? We need Y here, in fact, because we need to find the correlation, right? So if you are working with binary classification, you can just send the specific Y here. So it will select the most important features which are correlated to Y, right? So we will use this chi-square. Do you know more statistics? Do you know chi-square? What does it mean, chi-square?
Yes.
Can you say something about it?
It's just basically a statistics test that compares, uses the correlation to check. So you can have, let's say, a lot of inputs and check their relationship with them.
With the output, because we need to create mapping. And in fact, we need to find the correlation between inputs and outputs, right? So this tool, in fact, it will find this correlation and it will give us this chi-square score. So for solving this problem, I don't know what this Y is. Y here in this problem, we have 3 classes. So we try to find the inputs which are correlated to this feature using this. So this algorithm, it's a very nice tool, in fact. So in this case, we have those scores, and I want to select the best 2, because it's select K best, K equal 2. So in this case, I will select this one. I will select the third and fourth. If you want to select the best 3, for example, so in this case, we will select the first, third, and fourth features. So you can just try it. You mentioned, that you have a problem with 100, but you don't know which one is correlated with the output, correct? So you can just use select K-best, for example. There are many tools, but this one may be one of the simplest tools which we can use. And it would be nice, if you are writing a paper, for example, it would be nice to try to visualize your data, mention your data. You can select, okay, I will select the best 3, best 4, best 5. Train your model, test the performance, and you will see if, what is the impact. So in this case, I will select its third and fourth features, and I can use those 2 features for training my model. So now we are selecting, based on some correlation coefficient, not just by random. But when I trained, in fact, when I trained Iris before, I didn't select the most influential features for my model, but I just selected by random. But now we can select, and also it's useful for visualization, because now I can just use 2 features and ignore the rest, and I can use those 2 features for visualizing my model. Now you can run the Iris dataset one more time using, for example, first and second, correct, and third and fourth, and you can see the difference. Is there any difference in accuracy? We should expect better accuracy when we use the third and fourth features, because they are more correlated. In fact, more correlated to the target features. Do you like to go to the example and run it? Or should?
I think the class is soon over.
Yes, we will finish soon.
So maybe you will just
Okay.
continue with the slides and we can look
Yes.
at this.
I want to talk about BCA also. BCA, it's unsupervised. We will talk again about BCA with the autoencoder, in fact. BCA, it's unsupervised algorithm. So we are working with the features, not with the target features. We are working with X, not Y. So BCA, it's used for simplifications and data reduction or compression. We have also BCA from scikit-learn and decomposition. This one, BCA. So, but BCA, in fact, it does some transformation, right? We transform features from one scale, one dimensional space, into another dimensional space, right? Using eigenvector and eigenvalues. And the principal component, in fact, those are the eigenvectors. And they are perpendicular to each other. All those principal components perpendicular to each other. And we sort them in descending order using the eigenvalues. Eigenvalue, which is a variation, in fact, right? Or variance, using the variance. Which carry lots of variations or lots of knowledge. So I will do it also for, we do it for MNIST data set. So first, we got the MNIST, I normalized it, because each pixel value here, it's number between 0 and 255. I'm dividing it by the range. So now we are normalizing it. After that, I will use BCA, and I just asked the algorithm here to return 8 times 8, in fact, 64 principal components. Why it's 64? Because I want to display it as 8 times 8 matrix as an image. So I defined here PCA, and I want it to return 64 principal components, and I will fit it into my data. Remember, X, only X. We don't have Y because it's unsupervised. So we don't care about Y here because PCA is unsupervised algorithm, in fact. So we're just working with the features, not with the target features, only with the features. So this one, it will display the explained variance ratio. In fact, we have this graph to display the amount of explained variance. From this one, you can say, okay, if I will select the first 20, how much variance they will explain. If I selected the first 50, how much variance? Of course, you will not, if you will use a subset, you will not be able to explain the 100% variance, but it's a trade-off between number of principal components and the amount of variations which you want to explain. So we will get a reduced set. So the reduced set, we will get a reduced set from principal component analysis. I can use this reduced set for reconstructing. In fact, I can use inverse transformation to reconstruct the image. So if you are working with MNIST data set, I can reconstruct it using a reduced set, right? To just test this amount of explained variance. In fact, so this is the image. This is the raw image which we used, and this one it's reconstructed. In fact, using 144 principal components, right? So we got this is the original image, which is 28 times 28. This one also it's 28 times 28, but this one reconstructed using 144 principal components. And if you can see, it's still possible for us to know that this one is 5, this one is 2, this one is 0, this one is 1. So we can reconstruct the image using a reduced set of features, right? Of course, if you will increase this number, if this number is 784, what will happen? We will get the same pictures, correct? Because maybe this 144, it carries maybe 60% or 70% of the variation in my data set. So the constructed image looks like a noisy image, in fact. So I did SCGD classifier using 144 principal components. We got this result, and we got this accuracy. Star here means what? Yes, the star here, it means using 144. And without star, it's using the original set, original image. Do you see? So this one using 144 pixels, this one using 784. There is no big difference, in fact, in accuracy, correct? There is no big difference. So when we use principal component analysis, we try to work with a reduced set. We try to simplify the model. This model has 144 inputs. This model has 784. And there is no big difference. You see the numbers, there is no big difference. I used the same model, the same structure, but with a reduced set of features. And we can, this one, it's a little bit less than this one. But at the end, I mean, it's just, it's 90.3, this one 90.7. There is no big difference, in fact, in the accuracy, but this model, it's much, much simpler than this model because we are working with 144 principal components instead of working with a full set of features. So PCA also is, of course, it would be smart if we can use select K-based with this one. If we can use this one, for example, for MNIST, and select the most important 50 features, for example, and try to train a model, but this can be an exercise for you. So now we are training the MNIST data set using the full set, the first 100 principal components. You can use also K-best, because in K-best, we are not transforming it into another dimensional space, right? You have been asking about just what is the physical meaning. If you will use K-best, you will not change the physical meaning because I have a set of features, it's pixel values, and I will get the same pixel values, but I will sort them according to a chi-square score, for example. So it will have the same meaning. So if I have, for example, Emil is working in finance, he has a data set from the bank, he has age, income, and lots of numbers. If he will use select K-best features, the features will keep the same meaning. If it's age, it will be age, but I know that age is important than other things. For example, if I have a bike or not, right? So, correct?
Yeah.
It will have the same physical meaning if you will use select K-best, because select K-best, it helps me to just select the K-best features, but it will have the same physical meaning. But remember, if you will use PCA, you will get something totally different. And it will not have any meaning for your problem, because we transform it using, it will be the eigenvector because the eigenvector, it's different. I will have a new features, we call it principal components, but it will not have any feature, any physical meaning in my problem. So if I transform age and income using PCA, I will get something else, but it will not age, it will not be income anymore. It will be just transformation of my features.
It can be used, however, in image.
Principal components?
No, the last one when it's gonna change totally the.
Yeah, because we will select the most important pixel wise. We will apply it to the features which is pixel wise. So maybe it will help me to select the most important 100 pixels from my images. Correct? And you can, but I don't know if you can reconstruct the image or not using those 100 values, right? Because if you try to reconstruct and reshape it, maybe it will not have any meaning. But it's a good idea because I can put other features equal 0 and I can display it one more time and see do we lose any knowledge by ignoring? It doesn't transform it. Yes. So it helps us to just select the most important 100 values or features, but not transforming it into another dimensional space. Because PCA, we use eigenvector and eigenvalues. So the principal components, it's eigenvectors, right? So it's different representation of my features, but it will not have any meaning. And we need to keep this transformation all time. But if you will use select K-best, I will be selective, right? I'm collecting lots of data. No, I will ignore this one. Maybe I will just measure the most important ones. So if you are working in water lab, for example, so you can just say, no, we don't need this one, we don't need this one because we used the K-best before, and we know that this number is not important for me, this number is not important. Please, when you are in the next time, just select only those values, measure only those values. So maybe it will be economically better, in fact, right?
Do you have a practical example where changing the construction of these features doesn't matter?
Mm-hmm.
Like, for example, which application?
Which application and what?
For example, in finance, like we need to keep the construction.
So for example, I will just tell you an example. Maybe you are collecting data from customers, and so the bank he send an email to the people with a link, so they fill lots of information. Maybe those information it will be time consuming, and people will just give up because he asked me about if I have a bike or not, if I have a car or not, if I have maybe the brand of my car, maybe the color of my car, right? So he can send me lots of details which I need to fill in my details, and maybe it will be too time consuming, and people will just ignore it. But if you can use select KBest, for example, with the historical data, so now you know the most important values which I need to get from the customer, and I can send him only this set, because this is the most important for me. I don't care about your lunch yesterday. I don't care about your haircut. I don't care about maybe the color of your car, right? Because you need to get a loan. So you can have lots of information. I know you have been discussing about something, if you have a Facebook account, if you have a Twitter account, too much details, right? But using a KBest, for example, we can select the most important set of features, and we can ask the consumers or the customers to just fill in or answer very specific questionnaire, for example, and get the most important information from. So yeah, I guess Ricardo, yes. Sorry for we are finishing now, and I guess we finished already, Ricardo. Yeah. Sorry. So this is the first home assignment which we did last time. So please, there are lots of data sets, not too much, in fact. There are lots of data sets from China, from Russia. I tried to find any from Norway, but I couldn't find. So I don't know if we just try to find any data set, try to use OpenCV, try to, work together, please. Don't work by yourself. So try to work in groups. And we need to build a machine learning model to try to recognize maybe car plates. We need to get those numbers, right? To classify it. If you can get the car model and the car color, which is much easier. So I'm not expecting something very fancy and something very accurate, but we need to have a model which works. The accuracy is not very important. The most important is to build the pipeline, right? Data collections, data pre-processing, right? Building model selections, and evaluating your model. This is the most important for us at the moment.
Okay, Ibrahim, I have a question.
Yeah.
Like we need to make one model that does all the things, like it recognizes the plate, it recognizes the car model, it recognizes the car color, or we have to make different models for recognition of plate, one for recognition
it could be one model and it could be different models. So it's according to the accuracy. Just it's up to you to just do it. So
okay, because I was having this question because the data sets we are getting is one is related to car model and one is related to something else and one is related to plates recognition.
So one model for each one is fine, and we will apply those three models for each example. So when we have a car, for example, we will send the image to the three models. One will predict color, one will predict model, maybe one will predict will recognize the plates. So it's up to you. Just do it in any way. The most important is to get something working and running, but just do it in the best way.
Okay, thank you.
Up to you. Yeah. So thank you very much for today, because Ricardo will start his course in computer graphics. Thanks for joining us today, and we will continue next week. And next week we will be working with error bag propagation. We will implement it from scratch, step by step, and we will apply it also to Iris and MS. Thank you very much.